Okay, so good afternoon, everyone. Welcome to the CERIAS Security Seminar here at Purdue University. It's October 18th, and my name is Arvind Mikkelneni. I'm filling in for Professor Edward J. Delp, who unfortunately had a prior commitment he had to attend to. So today I will be introducing today's speaker, Nitin Khanna, who will be talking to us about forensic characterization of printers and image capture devices. So Nitin Khanna is got his bachelor's degree in IIT Delhi in India, 2005. Afterwards, he joined Purdue University, where he's currently working in the Viper Video and Image Processing Lab under the guidance of Professor Edward J. Delp. And his research is primarily in the area of camera and sensor security and forensics. So with that, I welcome you to introduce you to Nitin Khanna.
Hi. So the topic of the talk today is forensic characterization of printers and image capture devices. And I am Nitin Khanna. I am working with Professor Edward Delp. Here is what is the outline of the presentation. We are going to start with what image forensics is, why we need it, and then we are going to describe the general framework for device forensics. Then I will zoom into the area of cameras and scanners on which I am working in, and then my friend here is working on printers. I will quickly go through some of the results on printers. Then we finally conclude the talk. Device forensics. With the rapid advancement in the digital signal processing community, the cost of these electronic devices are escalating down very rapidly, and they are easily available to the consumers. The devices like CCD cameras are no longer just used in the scientific laboratories for radio measurements. They are available to the consumers at very cheap cost. So what these devices do? The devices interact with the environment and generate data. Like we have printers, we have cameras, mobile phones, and so on and so forth. Along with these devices, we have another set of tools available to us which help us to manipulate what the data they produce. Like in case of digital cameras, we have a number of image processing softwares like Adobe Photoshop and so on, which help even a novice to easily manipulate the images. So now there comes the need to have characterization of these sensors. What they are producing is the authentic thing or is a manipulated thing. So consider scenarios. In a sensor networks, we will be having a lot of nodes which will be capturing different data. Like we'll have a temperature sensing node, we'll have some cameras which will be giving us images, and these data will be transmitted over the network. Now we need to authenticate this data, that what we are getting is what the device has produced and not somebody has manipulated in between. Forensic techniques help us to uniquely identify these devices and characterize the manipulation, if any. Device forensics. By forensic characterization, we mean that given an observation of the device, say image from a digital camera, we want to know which camera has produced that image, or which scanner has scanned that document, and like things like that. These forensic characterization of devices help us to authenticate the devices and find out the make, model, and say configuration of the devices when that produce the data. That will help us to answer the question whether the sensor is trustable or not. Then these techniques can further be used for detection of forgeries, whether certain regions of the image is manipulated and what kind of manipulations are done, and things like that. So overall, we have some fingerprint for the devices which will help us to trace the data back to the originating device. Here is the device characterization framework, which we maintain that is fairly general, and it's not just applicable to the devices which we are describing here, that is cameras and scanners, but it's applicable to a lot of many other devices as well, like RF devices and so on. What we are going to do here is we design a suitable probe signal that goes through a device, say a sample image which we are going to capture with the camera, or a printed page which we are going to fire to the printer. And then this probe signal, after coming to the device, is sampled, and the sample response is picked to give us some features. These features will help us to characterize the device which has generated that information, that data. So here is what is happening at Purdue in this area. This is the web page of Purdue Sensor and Printer Forensics Group. There are three professors, Professor Edward Delp, Professor Elbeck, and Professor Chu. and here we can find out the publications and other related stuff. So these are the 4 devices which we are concentrating on presently: cameras, scanners, printers, and RF devices. My work is focused on cameras and scanners, so this presentation is going to be in detail about these 2 devices, but I have some results for printers as well. So digital images. Given any digital image, if we try to figure out which source has generated that image, we can come up with one of these 3 answers. It may be captured from a digital camera, or it may be coming from a scanner which has scanned an already existing hard copy of an image, or it can be generated by a computer softwares like Photoshop, or a graph generated by MATLAB, and things like that. So among these sources, we can have the images which are purely coming from cameras or purely coming from scanners. That is to say, a camera captured a scene and then we have not done any manipulation on that image. That will be classified as image coming purely from cameras. But there are further possibilities that we manipulated that image, we copied a certain portion of that image and pasted it somewhere else within the image, or we removed some portion of image, or we did some things like that. That will come under the class of joint camera and computer generated. Similarly, we can have cameras and scanners together, or scanned image manipulated by some computer software. So my problem here is to, given an image, identify the class from which it is coming. Image forensics. We talked about device forensics in general, and now what this image forensic is. The central question is, given a digital image, we wish to know which device has originated that image and if that image is authentic or not. Now the solution to this fairly big problem depends on what information we already have and what kind of information we want to get. In certain scenarios, we already know that this image can be coming from one of the possible cameras, or this is either a scanned image or a camera generated image. And then what kind of things we wish to know. Sometimes we wish to know what exact camera has produced that image. Or the other question may be which make of the camera has produced that image. Or we just want to know the class of the image, say if it is camera generated or scanner generated. Other scenario can be in court, we just wish to know whether this image is authentic or not. We don't wish to know the exact manipulations which are undergone on the image, but we just wish to know its authenticity. So there are a lot of different kinds of questions which can be raised, and the solutions to those questions will depend on what a priori information you already have about the images. These are the 3 main problems which our research is focusing on. First of all, we wish to know the source of the image, that is image source identification. That is to say, we have an image and we wish to know whether it's a scanned image, scanner generated, or a non-scanned image. Then we have second problem of source camera identification. We see in the second problem we have this a priori information that this image is a image generated by digital camera. We wish to know which exact camera has generated that image. And then in the third problem, source scanner identification, we have similar a priori knowledge that this is a scanned image. This has been scanned by certain class of scanners, and we wish to know that which particular scanner has scanned that image. So to solve the problems mentioned, we have to know details about the devices, how they work, what kind of signal processing operations are done inside them, and what are the physical components involved, so that we can use those differences and similarities to solve the 3 problems which we mentioned. We'll describe about digital cameras, scanners, and printers. Let's begin with the camera. All of us are familiar with this digital camera in one form or the other, and these are the different physical components of the camera. The most interesting part of the whole camera is, for us, at least for this purpose of classification, is the CCD, or imaging sensing. The CCD can be replaced by a CMOS sensor, and this is the heart of the camera. On the back view we have LCD, which is the main component, which led to the rapid replacement of these digital cameras by the their analog counterparts will get replaced by their digital counterparts. Because in analog cameras, we have to wait till the image is finally processed and we get the final outcome to see what image we have captured. But in digital cameras, we have the immediate feedback, what the final image is going to look like. Here is the most interesting part, which we will be using, is the digital camera's image processing pipeline. The light originating from the original scene goes through a number of different complicated paths to finally give us the image which we store on our camera in the form of JPEG or TIFF image. First of all, the light passes through a set of lenses, the purpose being to focus the light on the imaging sensor. Then this light passes through a set of filters, main of which is anti-aliasing filter and infrared blocking filter. Then the light reaches the imaging sensor. In between the imaging sensor and the filters is CFA or color filter array. I will explain in a minute why we need this CFA. Then finally our CCD or CMOS gives us voltage values corresponding to the light intensity falling on it. We need to digitize this voltage value and finally store them in user specified format, say TIFF or JPEG. Now for imaging sensor, we can have either CCD or CMOS. Those are the main sensors used, and CCD cover the major portion of the market presently because of their good quality. Now this CFA. Our imaging sensors, CCD as well as CMOS, both are, so to speak, colorblind, in the sense that they just count the photons which are falling on them. They don't have any way to discriminate which wavelength of the light they are interacting with. So if we have just one CCD or CMOS sensor, then we will be producing basically a gray level image. We don't have colors in it. So to get the colors, one possible solution looks like we can have 3 CCD or CMOS sensors, and each one, the incoming light will be broken into 3 parts corresponding to R, G and B, and each one will capture one of the colors. But this solution is not practically feasible because the imaging sensor is the most expensive part of the camera, and we can't afford to have 3 sensors to make the camera still on the consumer end. So what is the solution? The solution is offered by color filter array. Color filter array is basically a set of filters where each pixel is now assigned a particular color. What we do is we filter the light reaching the particular pixel so that every pixel is just measuring one of the colors, say red, green or blue. We can have different kinds of CFA patterns. We can have in the YMCG space or we can have in the RGB space. The RGB one is the most common, and then we have at every pixel only one color information. So to get the other 2 colors, we need to go through some kind of interpolation algorithms which will give us the values of other 2 colors at every pixel. And there are a lot of different CFA interpolation algorithms existing, and depending on that there are certain image forensic techniques which tend to use these differences in the cameras to figure out which camera has generated a particular image. Our focus is with the noise. As with any other sensing device, these CCD or CMOS sensors have also some noise incorporated with them. Here in this model, the Xij is the value of the ijth pixel of the original scene which we want to capture, and neta ij is the photo response non-uniformity noise. That is a kind of multiplication factor which comes here because even if we are capturing, say, uniformly lit scene, we are not going to have the pixel values which are exactly same over all the CCD, because due to the manufacturing defects intrinsic to the process of manufacturing, different pixels in the CCD have different responsivity. Then we have an additive noise epsilon ij which corresponds to the FPN, fixed pattern noise. The source of fixed pattern noise is basically dark currents. By dark currents we mean that even if we have no light falling on the imaging sensor, we are still getting some output, and that corresponds to the dark current noise. So, and then this f represents a nonlinear function which incorporates all other operations done that we mentioned earlier, gamma correction and color, other things like that. So the main noise of the CCD which we are concerned with are fixed pattern noise and photoresponse non-uniformity, PRNU. These two components are fairly constant over the frames. That is, even if we are using the same camera to capture different images, these two components will be having a constant values. And together they are sometimes called pattern noise, with which we are concerned. So we wish to utilize this pattern noise to differentiate between different cameras. Let's see how. Now the problem, if we see here, before we get the final image, we have a non-linear function operating on the captured values and the noise. And in most of the consumer end cameras and even scientific cameras, we don't have access to the raw data, that is before those non-linear operations. They just store the final JPEG or TIFF image. So it's not possible to recover that pattern noise using some kind of process like flat fielding, where we capture basically uniformly lit scene and then solve that equation to get back our pattern noise. So we have to find out a way around it. What people are doing is, if the average number of images captured from a single source, we will be left with mostly the pattern noise, which is constant with all the frames. To speed up this process, we can first do the denoising of the image. What we'll do, basically we'll use certain kind of denoising filters, and then we'll subtract this denoised image from the original image. That will give us the noise corresponding to that image. And if we average these noises, we will be essentially eliminating the random components and enhancing the fixed component of the noise. That way, by averaging the estimated pattern noise across many known images which are coming from the same source, we will have the pattern noise corresponding to that source. Then these patterns can be used in the classification step to classify an incoming image whose source is unknown. See the block diagram of the same process. We have a set of images which are coming from the same camera, and we denoise it and extract the noise corresponding to those images, and then we average all these noise patterns to get the camera reference pattern. The assumption in the solution of this problem is that whatever the image which we are going to test on is coming from one of the cameras on which we have already trained our classifier. So we have already a set of camera patterns, and we have an unknown image coming to us. We'll do the noise extraction on it, and then we'll correlate this, find the correlation of this noise pattern of the unknown image with all the existing camera patterns. And finally we will decide on the basis of which camera is giving us the maximum correlation value. That way we will pick up the camera among one of them who has generated the image. Here is our experimental setup. Yeah.
Have you guys done that then already? Has this been done?
Yeah, this has been done. Not only us, but some people outside also are trying similar techniques to do the camera detection.
How does, if you apply steganography, how does that affect the image? Have you checked that out? Or have you?
Yeah, if that question we can deal at the end, because there are a lot of things which you can do. The basic simplest thing you can do to for this technique not to work as it is, as in done in watermarking, you can desynchronize the noise pattern. So you can extract the same noise pattern and shift it by 1 pixel here or there, or you can remove the noise pattern. That way you can easily avoid detection by this kind of approach, simple approach. We need to have some way around that thing. And there are a lot of other things which you can also do. So our experimental setup, which the results I am presenting here, is we have 4 cameras, and we captured around 300 images from each of those cameras. 2 of them were of the same company, Nikon, and then we have Canon and Panasonic. Then we find out the reference pattern, as I told earlier. And in the classification, we do the classification of the rest of the images. Those are separate from the training images. We did training on 100 images and testing on 200. So this is the result. In this graph, the y-axis has the correlation values corresponding to different pictures with different camera patterns. X-axis has the picture number, and the first of those 100 images are basically training images, and then we have testing images, the rest of them. These cross marks in green color are the correlation values corresponding to the Nikon's camera pattern, and as we are clearly seeing that these values are much higher than those correlation values corresponding to their cameras. So this technique gives us an average accuracy of around 99%. Here is similar result on Panasonic camera. Here also we are seeing that we have a clear demarcation of two classes, and we can find out which camera has generated that image and achieve accuracy of 98%. So this is about source camera identification. Let's now move to scanners. If we closely look at this scanning system, it will be easily seen that it is very similar to the camera scanning pipeline. We have an original placed on the glass plate, and we have a light source and lens system. This light source sends the light to the original, which reflects the light, and the reflected light is focused on the imaging sensor, which can again be CCD or CMOS. So if you look at that, we have a similar structure here. We have a CCD, and we have the lenses and filters, and we have similar things here. Now there are certain subtle differences also which we should keep in mind while designing our system. The imaging sensor used in the scanner is not a two-dimensional grid, as was the case with the camera. And this linear imaging sensor is translated with the help of a motor over the whole image to give us the complete image. And the second major difference is, whenever we capture an image with a camera, we are basically using the complete CCD array. But when we are using a scanner, most of the time we are using only a portion of this linear sensor array. Let's see how we can use these things. So since the heart of both the things is CCD or CMOS image capturing sensor, so they are expected to have similar noise characteristics. That is, we will have a similar model as we have here in case of cameras. So if we use similar characteristic and use scanner's noise as fingerprint for the scanners, we should be able to identify the scanners. One thing to be noted, as I earlier pointed, is that here a linear sensor array is translated over and over to generate the complete image. So every row of the noise extracted is expected to have similar characteristics. So what we do in our preliminary experiment, we scan a number of photographs with 4 of the scanners at the native resolutions. That is, for 2 of them was 1200 dpi, and for the other two was 4800 dpi dots per inch. And then we divide these complete images into small blocks of sizes 1024 into 768. We maintain here that these blocks B0 and B5 and others in the same column will be having similar noise characteristics, because basically they are generated by the same portion of the sensor. And these blocks B1 and B6 will have a different noise characteristic compared to B0 and B5. So effectively we can treat them as 2 different sources, and we want to discriminate between these 2 sources. So here is a similar training phase. We have these images, we do the noise extraction, and we do the averaging to find out the scanner reference pattern. And then we use these scanner reference patterns in the classification phase. For source scanner identification, we have the unknown image. We do noise extraction and correlate with all the existing scanner patterns in our database. And the pattern which gives us the maximum correlation is determined to be the source of the scanned image. See the results on it. We have 2 scanners, HP Scanjet 6300, two of the same model and configuration. That is, and this HP Scanjet 1 is basically the first column of the first HP scanner, and then we have HP Scanjet 2 which is the first column, the second HP scanner, and we have one UMax scanner, which we also divided into 2 columns. So effectively we have 6 sources, and we want to differentiate between these 6 sources. And here are the results. So this ends our source scan identification. Let's go to the next problem which I told earlier. That was image source classification. Here, as I mentioned earlier, we want to utilize the difference in the geometry of the imaging sensor. In the case of camera, we have a 2D imaging sensor, and in the case of scanners, we have a linear imaging sensor. So digital images captured with the camera will be having a 2-dimensional noise pattern, and since as with every sensor we have the incorporation of noise in the measurements done, so we can divide this noise into 2 portions, this random component and the fixed component. By random component, what we mean is the portion of the noise which is not constant over the frames captured or documents scanned, and the fixed component is that component of noise which is going to remain fixed with different scanned documents. So for the scanner, the linear array is translated over the complete picture to give us the complete scanned image. So we will be having a periodicity in the noise extracted from the scanned images, corresponding to different rows of the scanned images. While there is no reason to expect similar behavior in the columns of the noise extracted, because those columns essentially correspond to different sensing pixels. On the other hand, with the digital cameras, there is no reason to expect neither in the direction of columns nor in the direction of rows these periodicity in the noise patterns. So the basis of our classification technique is the difference in the geometry, which lead to the differences in the characteristic of the noise pattern. Okay. So we do the noise extraction, we have the image, we use a denoising algorithm. Currently we are using a wavelet based denoising algorithm, and then we get the noise corresponding to that image. Now we extract certain features from this extracted noise and send it to the already trained SVM classifier that tells us whether this image is coming from a scanned class or the non-scanned class. Now what are these features? What we do is this n sub k represents the noise corresponding to the image I sub k. After doing the denoising and subtraction, we found out the average of this average row of this noise, and similarly we find out the average column with this noise pattern. And then what we do is we correlate this with this average row with all the other rows of the noise, and made a vector row correlation, and similarly we made a vector column correlation. What is expected that these row correlation values will be much higher than the column correlation values in case of scanners, but not in case of cameras and images generated by computer softwares. So here is how we use correlation, and then we have the feature vector, which are the first order statistics of this row correlation and column correlation. We take the mean, maximum, minimum, and standard deviation of these 2 columns of vectors. That way we have total 8-dimensional feature vector corresponding to every image, and we send it to the classifier that tells us which class they are going to belong to. And here are the results. We use around 3000 blocks of scanned images. I am saying blocks here, not the images, because we dive into the blocks. And scanned images and images from 3 cameras for the training purpose, and then we tested on 1000 scanned blocks and camera images. And this is what the results we got. We are seeing that we are having around 98% accuracy for the scanned class, going into the scanned class, while we have around 90% accuracy for non-scanned class going to non-scanned class. And that's pretty good. So this ends our discussion on image source classification, and now we will begin our discussion about printers. What kind of techniques we can use for printers, and a quick review of the results what we already got. Printers. First of all, I will describe the intrinsic techniques which can be used to identify printers, The main source of these intrinsic features are the imperfections in the printing process. Like one major portion of which is banding. This banding occurs when, say, we are printing a constant gray level patch through a printer. We are not going to get a constant gray level patch as the printed page. We will be observing some fluctuations in the intensity values. And these fluctuations can be some kind of sinusoidal variations. So what's the origin of these variations? In the printing process, basically there are a number of rollers which support the paper and toner and things like that, and all of these are controlled by a single motor. So these fluctuations in banding basically correspond to the frequency on which these fluctuations are occurring in the motor. So like every printer is expected to have a certain characteristic frequency which can be used as its intrinsic signature. For forensic characterization of printers, we have two kinds of techniques depending on what kind of documents we are dealing with. We do banding analysis on halftone images, and we do texture analysis on text printed. Basically, in banding analysis, we take a horizontal projection of the whole printed paper and find out the FFT of it, and that gives us the frequencies at which these fluctuations are occur, and based on that we can figure out which printer has printed that page. Both of these techniques are using intrinsic features only, because we are not embedding anything actively into the printed page. We are just utilizing what is there in the printing pipeline already, and we have achieved the accuracy around 90%. That holds on different paper types and consumable age. So for the banding analysis, we are taking the horizontal projections, but for the texture analysis, we extract out certain portions, region of interest from the printed document, and we extract certain features from each region of interest. Say we extract out the characters E, and for every E, we found out the features. This GLCM stands for gray level co-occurrence matrix, which is basically second order distribution of the gray levels. This is how we found the GLCM. And then we extract these features from this gray level co-occurrence matrix, which are used by our SVM classifier to tell us which printer has generated that image. Classification method. What we do, we extract out the characters E print on the printed page. E because E are the most frequently occurring characters, and then for each of these E, we generate feature vectors independently, and we send each of these feature vector to our SVM classifier. So we have classification results for the number of E's present on the paper, and then we finally take a majority voting to finally tell us what is the printer which has printed that page. For SVM classifier training, we have used 5,000 known features. We have printed 500 E's from each of the 10 printers, and then we have an independent test set to test the accuracy of our system. Printer characterization. This matrix here shows what kind of accuracy we are getting. We used 22 features, and we printed 300 E's on each of these from each of these printers. Say the value in this corner here represents this 296 represents the number of E's which are coming from the first printer and classified as coming from the first printer, and the two next to it are the E's which came from the first printer but they are classified as coming from the second printer. So the diagonal values basically tell us what are the number of E's which are correctly classified, and if we take a majority voting, we can clearly see that we will get accurate answers about the printers which have generated that image, which has printed that paper. Now, the second thing we can do is we can extensively embed some signatures in the printed page. What we do here is we modulate the EP process to generate banding signals. Earlier we are utilizing the banding signals which are characteristic to the motor present in the printer, but now we can embed our own banding signals to tell us which particular printer has printed that paper. We can embed the printer's name and maybe the date of the printing, and possible sources of generating these banding signals is laser intensity modulation, or we can control the motor, or we can do the laser beam steering. One of the ways to do this extrinsic signature embedding is laser exposure modulation. What we do here is we control the intensity of the lasers in some sinusoidal fashion, which will effectively lead to different dot sizes. Say we are varying the intensity of the laser beam in a sinusoidal manner, we will be having the dot sizes varying in a sinusoidal manner, as we are seeing here. And we can pick up these periodic signals to find out what kind of moderated signal is there on the laser beam, which will tell us effectively which printer has printed that image. Here we are showing the results. The image on the left top corner is the original image, original printed image, and on the right side we have the image on which 4 different frequencies are embedded on the laser beam. Then we have the FFT of the horizontal projection corresponding to these 2 images. As we can clearly see that we are able to identify the 4 frequencies which we embed on this image. But from the visual point of view, there is no difference in these 2 images. But we have embedded 4 bits of information here. Now this was for about continuous half-tone images. But what about texture? We can't use similar FFT analysis for the text, printed text, because texts are saturated regions. So what we have to do here is we have to see at the edges. Say we look at this edge of this eye. The first eye printed here is without any modulated signal, so its edge is straight. But we see here these edges have a sinusoidal variation, they are not straight. And this sinusoidal variation is basically coming from the dot size modulation which we are doing by changing the intensity of the laser beam. So we can, here is one of the examples where how we can embed bits of information on a printed paper. Like in one line we can have a modulated signal corresponding to no modulation, and then we have different frequencies of modulation. So effectively we are embedding 1 bit of information in each of these lines. And finally we can embed in these bits the printer's unique identification code or the date on which this has been printed. So this is what we have described till now. We described source camera identification, how we can use the pattern noises of the camera, CCD or CMOS sensors, for classifying the cameras or identifying the particular camera from which the image has been coming, assuming that the image is coming from one of the cameras which is already in our database. Then we described that how this similar technique can be extended to scanners, where we have similar CCD or CMOS sensor as the main component, and we have shown the results. Then we have image source classification depending on the differences in the geometry of the devices. Imaging sensor, we have a linear sensor in one case and we have a 2D sensor in the other case. That allows us to discriminate between the 2 devices, scanned and non-scanned images. And we have shown the similar kind of how these intrinsic and extrinsic techniques can be used for printer identification and what kind of results we are going to get. I would like to save the next slide of future discussion, and before that I will ask some questions anyone has. Yeah.
The software you've written for this, is it portable across different cameras? I mean, if you apply the same algorithm to different, does it work?
Yeah, it will work provided we have to have the training set. If we are giving an image which is not coming from the one of the camera which is in our database, then we are not going to classify it correctly. Yeah.
Okay. Is the denoising algorithm well known, or did you guys write it?
No, it's one of the denoising algorithm which gives pretty good denoising performances, that is wavelet based, and it's not particular that we denoising algorithm only. If we have a better denoising filter which can support us giving the fixed pattern noise, so basically that question comes to
Actually, right now we're using a wavelet-based denoising filter ourselves, based on some prior work which has been done on the forensic characterization, and we're currently working on some manure denoising techniques, which are current. So, does that answer your question?
Yeah.
Yeah.
basically that will depend on how we model the noise, and different denoising filters will help us picking up different kinds of noises models. Any other question? So let me go ahead to the future work. What we describe certain models of the devices and how these models help us to classify different devices into different classes. And we described an algorithm for image source classification. But that algorithm essentially dealt with only two classes, scanned and non-scanned images. We wish to extend this work for three-class classification, where we can figure out whether it's a scanned image, a camera-generated image, or it's a computer-generated image. And then we used to use these techniques for authenticity detection. And there is one of the questions was that whether these techniques work when we have manipulations. That's another agenda we have, that test these techniques, how well they work, and what modifications can be done in them to make them work in case of we have manipulated images. And if those techniques work in those scenarios, then we will be interested in the finding type of manipulations done, and maybe the region of interest where the manipulation is done. Say a certain region of the image which has been copied from another image and pasted there, or a certain region of image which has been blurred or removed from that image, and things like that. So, any other questions? No questions?